Let us discuss today one more important chapter for JEE, that is atomic physics. In fact, in this particular topic, we people have to discuss about electrons, the so-called cathode rays, photoelectric effect, the applications of photoelectric effect, and other important features related to that. In addition to that, we are going to take up the concept of X-rays, Compton effect, and de Broglie's hypothesis, that is dual nature of light. That of course a little later we are going to discuss about. Let us first of all take up from the very beginning of this topic. In fact, every time, every year I am talking about, they are asking quite a good number of questions based on atomic physics as well. And one of the easiest most chapters what we are having, and easy to understand, easy to remember, and very easy to reproduce in the examination. That's why try to just concentrate on this particular topic a little carefully, so that this chapter will fetch you few marks in the final examination. Out of this topic, as I have already told you, we are starting from the concept of cathode rays. Truly speaking, cathode rays, when we talk about, they are negatively charged particles. Whatever equations we have discussed way back in electrostatics topic, when a charged particle is entering into an electric field, or a charged particle is entering into a magnetic field, what is the force that it is going to experience either in electric field or in magnetic field? All these concepts whatever we have discussed earlier are going to be once again true and correct for this particular cathode ray. Therefore, if you are thorough with those formulae, you can work out almost every question that has been asked on cathode rays as such. Another important feature is try to concentrate on two areas. One, the E by M of cathode rays. The value of course is known to you all, 1.76 into 10 power 11 coulomb per kg. That particular value has been determined by J.J. Thomson. So that experiment you people should know. And secondly, to calculate or estimate the value of charge on an electron, Millikan's oil drop experiment is one which already you might have studied. So these two concepts are to be remembered very, very carefully. So with all these, let us start taking up the problems from this particular chapter, atomic physics. As and when we come across some theory related to that particular problem, I will just give you that one then and there itself, so that you will be able to understand how we can correlate the theory with the values given in that problem as such. Let us start with the first problem what has been asked here. The very first problem, let me read it out first. An electron is accelerated through a potential difference of 1000 volt. The velocity acquired by the electron is how much? In fact, such model questions we have even discussed way back in the chapter called electrostatics. Now once again we are having a similar model here. Let me read out the answers first of all what have been given in the form of options. The very first option is given 2 into 10 power 8 meter per second. And the second option is given as 1.88 into 10 power 7 meter per second. And third option is 1.5 into 10 power 7 meter per second. And fourth option is again 1.5 into 10 to the power 8 meter per second. So what is the correct option over here? We just have to look into. First and foremost, electron is accelerated through a potential difference of 1000 volt. That is the data provided to us. Whenever an electron of charge E and mass m is entering into an external field having a potential difference capital V. Observe this point carefully. An electron of charge E, mass m, is entering into an external field having a potential difference capital V. Then the kinetic energy acquired by the electron will now be EV joule. All of you can understand the kinetic energy acquired by the electron in that external field having potential difference V, that is E into V joule. What is the formula for kinetic energy? All of us we know, half mv square, that now is going to be EV. This small v refers to its velocity and capital V refers to the potential difference what has been applied in the form of external field on that electron. So you can understand from this particular formula, V is equal to 2 EV by m whole under root. That is the formula based on which you can solve this problem. Under root 2 EV by m, out of that every value is known to you. Charge on an electron is 1.6 into 10 power minus 19 coulomb. And potential difference has been given in the problem as 1000 volt. And mass is known to you all as 9.1 into 10 power minus 31 kg. These two are standard values for an electron. If you don't want to write them individually this way, you can directly remember the specific charge on an electron also. What is specific charge? It is a charge to mass ratio. That is what we call it as a specific charge. So what is the specific charge value E by m? E by m directly also you can write as 1.76 into 10 power 11 coulomb per kg. Even you can substitute in place of E by m directly this value also there. It is left to you which one you prefer doing it. Whatever be the case, this is the way we people have to solve that. Now, when you just look at this calculation, the simplification of this one, if you make it, this of course 10 power minus 9, it goes 10 power minus 12 times here. Minus 12 when it goes up, it becomes 10 to the power 15 totally. So 32 by 91 into 10 power 15. So you can just simplify that one. Your answer will be something like some value into 10 power 7. What is that value over here? It's nearly 1.88 into 10 to the power 7 meter per second. This is the value. But only point you should understand is whenever any charged particle, I am not talking of electron alone, any charged particle having some charge and some mass m, when it is entering into an external field having a potential difference capital V like this, then the kinetic energy acquired by the particle would be EV joule. This is the formula based on which I have written this equation and from which I have estimated what is the velocity of that electron now. It's around 1.88 into 10 power 7 meter per second. One thing also you can remember in this regard. We all know velocity of light is in the order of 10 power 8. In fact, 3 into 10 power 8 meter per second. We know that. Velocity of electron usually is very close to that value but not 10 power 8. So roughly around 10 power 7 in that order we can get that answer. So generally speaking, second option or third option, one out of the two you can estimate. So in this particular calculation we have got the correct answer as the second option itself, that is B, what has been given as 1.88 into 10 power 7 meter per second. This is the first problem what we have picked up here from this atomic physics part of it. Let us check the next number now. That is problem number 2. In Millikan's oil drop experiment, a drop of charge Q and radius r is in equilibrium between two plates having a potential difference of 800 volt. Then the charge on another drop of radius 2r, which is kept constant with a potential difference of 3200 volt, is how much? In fact, we have been given once again 4 options. The very first option is q by 2, second option is 2q, and third option is 4q, and fourth option is q by 4. So 4 options have been given. We have to decide what is the correct option out of the 4 given. First of all, let me just remind you in brief, what is it we people have done in the case of Millikan's oil drop experiment. We will be finding 2 parallel plates like this, in between which we will be finding the oil drops which have been rather sprayed onto the topmost plate they enter into. Now the concept here is this particular droplet, whatever is in between the plates right now, is in equilibrium. That is the condition what is mentioned there. In fact, you people all know very well, in that particular experiment of Millikan's oil drop method, you would be finding that the electron attaining terminal velocity. Attaining terminal velocity means it is very clear to say that the particle or that so-called oil droplet will now be in equilibrium. The downward force acting on it and upward force acting on it both are equal and opposite. In fact, the same concept has been given over here. A charged drop having a charge q and radius r is in equilibrium between the 2 plates when the potential difference is 800 volt. That is the concept. So first of all, when I consider this is the droplet, you can understand weight will be acting downward, and force due to that electric field I will be finding acting on the same particle upward. So the so-called weight in this particular case of this droplet, that is now being compensated by that force which is caused by the external electric field that is applied on that particle. So as long as these two are equal, what we can predict? The particle may either be at rest or may move with uniform speed, but definitely the particle will never have acceleration. So what we can understand, that is a condition for us to say that the particle is in equilibrium. That is the concept. Now let us equate these two. First of all, EQ must now be equal to mg. But in this particular problem, he did not mention the mass of the particle anymore. But he has given us a clue. What is that? Radius he has mentioned. So what can we write now? This E, we can write it as V over D. What is this V over D here? You can understand D is the distance of separation between the 2 plates across which the external electric field has been applied. And what is this V now? Potential difference that has been applied across the plates, parallel plates. So V by D times this charge what has been given as Q for us in the problem. That capital Q is equal to M, means I can write 4 by 3 pi r cube, that is volume, into rho, that is density, into acceleration due to gravity, as usual I have taken. So what we can understand here, EQ is equal to mg, the formula. Out of that, E I have written it as V by D, that is potential difference divided by distance of separation between the parallel plates across which the electric field has been applied, into the charge of the particle, is equal to mass being volume into density, 4 by 3 pi r cube into rho into g. Rho is the density of that liquid of which that oil drop has been taken up now. That liquid means that oil only. So rho is the density of that oil of which the drop has been considered here. That is the point. Now look at carefully here, please. he is changing the value of potential difference. Where from 800 volt to 3200 volt he is changing. Fine. What else he is talking? He has changed the radius of that one. That in the sense what he has taken another drop of radius 2r this time. Earlier it was only r. Now it is 2r. So what we can understand, first of all, d is a constant, that is the separation distance is same. 4/3 is constant. Pi is constant. Rho is constant for that oil. And G also is constant at that particular place where we people are performing that experiment. Now observe carefully how many terms are not circled there. In fact, 3 terms I have not circled them. Those 3 only are the variables right now according to the problem given. So what we can write now? This implies charge on the droplet is directly proportional to r cube by v. That is actually the formula you people can directly get by equating these two values. Now, when you are comparing the charges on two different droplets, how to rewrite this formula is known to you all. I can write q1 by q2 is equal to r1 cube by r2 cube into v2 by v1. r1 and r2 are their respective radii. And of course, v1 and v2 are the potential differences applied across the same system. Now we can write q1 is given as q for us. q2 is to be calculated now. r1 is given as r. You write r cube. But what is r2? Double the radius he has given, 2r whole cube. You can write that one 8r cube as such. Into what is this v2 that has been mentioned in the problem? 3200 volt has been given here. And initially the potential difference was only 800 volt. So according to these values, if you can cancel these two off, right, now you will be getting this one going 4 times, right, and that 4 once again goes here twice. So what is ultimately left over? 1 over 2. So cross multiplication now gives you that q2 is equal to 2q. So the charge on that droplet, of which the radius is twice r, that is twice that of the original drop what has been considered, is now going to be twice the charge on the first droplet as such. So you can say q2 when it is 2q, see the options what have been given, I have already read earlier. q by 2 the first option, 2q the second option, 4q the third option, and q by 4 the fourth option. What is the correct option now? You can guess directly. So it is the second option which is going to be true again. So option for this one is B again. So what you should understand here is what is the condition for equilibrium of that droplet between the parallel plates in the case of Millikan's oil drop experiment. Only point you should understand here is the weight and the force due to electric field both are supposed to be compensated by one another. So by taking that only, I just have arrived at the relation between charge on the droplet, radius of the droplet, and the potential difference which has been applied across the plates of that particular apparatus. So if you take that Q is proportional to R cube by V, the moment you people have come across this relation, the remaining is simple calculation only, nothing special over there. So this is the method you people have to adopt as far as the second problem that has been based on Millikan's oil drop experiment that is concerned. So that is your second problem as such here. Let us check the next number which also is based on Millikan's oil drop experiment only. An oil drop of mass 4.8 into 10 power minus 10 gram and charge 2.4 into 10 power minus 18 coulomb stands still between two charged horizontal parallel plates separated by a distance of 1 centimeter. Observe the wording carefully. Standing still means what? It stands still, he said. Standing still means nothing other than the particle is in equilibrium. It is not moving from its position of rest. That means initially it might have been moved due to its weight in the downward direction. But as and when people have applied some external electric field between those two parallel plates of Millikan's apparatus, that is, the particle is now at rest. It is standing still. That's what has been mentioned. So one can understand that it is in equilibrium. Fine. Then what next he is asking? If now the polarity of the plates is changed. Polarity, that means the positive plate has now become negative and the negative plate has been given positive charge. Like in the sense, I have just interchanged the terminals of the cell across the plates like. That's what you people have to understand. The polarity of the plates is changed. Then the instantaneous acceleration of the drop is how much? Instantaneous acceleration. At that instant of time when we have changed the polarity of the plates. What is the acceleration? That's what he is asking. And of course, he gave us one value, that is acceleration due to gravity. He is asking us to take that value as a 10 meter per second square. That is the concept. And 4 options have been mentioned once again here. Let me read them out. First one is 5 meter per second square. Second one is 10 meter per second square. 10 meter per second square is as well equivalent to acceleration due to gravity over there. And third option is 20 meter per second square, and fourth option is 40 meter per second square. So 5, 10, 20 and 40 all in meter per second square SI units he has taken up. So this is the question. Firstly, what is the point on which we have to focus? Look at that one. The particle of some mass and charge stands still between the two parallel plates, horizontal parallel plates, separated by a certain distance. That means immediately you should get to your mind that when this is the particle what I am talking about, its weight that is going to act downward, we know, and upward force whatever that is acting on this one should now be due to the electric field which has been applied between the plates. So you can understand this is weight and this one is the force due to electric field. It is a standing still, he said. Standing still means what? We now can write EQ is equal to mg. That is the condition for the particle to be in equilibrium. But what he is logically asking you the question you look at now. No doubt according to the first sentence, what has been mentioned in the problem, you can come to this conclusion that upward force due to electric field and downward force due to the weight both are equal. So that is what only I have written here. EQ is equal to mg. Hope you might have understood the first part. Fine. What is now the second part of the question? Read it carefully. If now the polarity of the plates is changed, polarity is changed. That means what happens in the second case, you know, if I take this is the particle, no doubt its weight will be acting downward only. That you and I need not have any sort of a doubt towards that. Because always weight of any particle or any body, that always is going to act in the downward direction, that too towards the center of the earth. So weight part of it will be downwards only, no doubt absolutely in it. But what did he say now? When the polarity is interchanged, the charges are being changed of these two plates, then the force due to electric field also acts downwards on this particle now. Why? Because earlier suppose the particle was going up due to electric field. Due to weight it is coming down. Both simply since they are equal, the particle is at rest there. Fine. The moment you interchange the terminals of these two plates, or if you are changing the polarity of the plates, then force due to electric field also will act downward now. In addition to what? In addition to its own weight. Weight anyhow is acting downward. There is no problem for that. Now even this EQ also, that is a force due to electric field also, is going to act downward in addition to the weight of the droplet. Then what would be the effective force now, or the net force that is acting on this particle right now? Net force in which direction? Downward direction, because there is no compensating force acting upward. When there is no compensating force acting upward, the net force which is acting downward on the particle will make the particle accelerate downwards now. So you can definitely understand the net force in this particular case will be EQ plus mg. Since both are in the same direction, I can take the net value of force acting on that droplet as the sum of these two individual forces. The moment you write EQ plus mg, but numerically we have got in the first equation EQ is equal to mg earlier. So numerically they are equal. Now they are acting in the same direction, therefore we are adding them to get the net force on that particle. So what can I write now? In place of EQ, I can write 1 mg. The other mg already is there. So what will now be the total force acting on that droplet in the downward direction now? It is 2 mg. Now this is the net force acting on that drop or droplet, whatever you talk about. Therefore, what is the question he is asking? What is acceleration of the particle? Acceleration of the particle. You definitely can understand acceleration is net force divided by mass of the particle. What is the net force we people have got? You know it. It is 2 mg. So I now can write this one as 2 mg divided by mass of the particle. If I take it as m, this m gets cancelled. I am left with 2g, that is equal to acceleration. But already in the problem he has mentioned acceleration due to gravity's value. He is asking us to take its value as 10 meter per second square. Otherwise we have to take only 9.8 meter per second square value. We all know that. Therefore 2 times 10 you can directly write 20 meter per second square. That is supposed to be the instantaneous acceleration of that particle when the polarity of the plates, that is, interchanged. That means already g value is given 10, therefore it now becomes 20 meter per second square as such. See the options now. First option 5 meter per second square, second is 10 meter per second square, third is 20 meter per second square. So automatically we can come to the conclusion that the answer for this particular question is the third option. So only thing you should understand in this problem is you should divide this problem into 2 parts. When it was still or in equilibrium, then upward force becomes the force due to electric field and downward force becomes the weight of the droplet. So both are numerically going to be equal according to the first half of the problem. The moment you are interchanging the polarities, automatically you will be finding both the forces acting in the downward direction. Therefore net force becomes the sum of these two. Out of them EQ and mg are numerically equal. So that if you write it here, you get the net force as 2 mg and automatically acceleration becomes 2g, which now becomes 2 times 10, that is 20 meter per second square. Hope all of you might have followed this model, one of the excellent model questions what we have here. So that's a point you have to remember. So this is problem number 3. The option for this one is 20 meter per second square, which is the third option for us. From the next problem onwards, few model questions we have taken up from photoelectric effect. Just before taking up that slot, let me just remind you 2-3 points. Photoelectric effect is that one in which you find light of suitable frequency when it is incident on a metal plate. That metal, which of course we call it as photocathode, it now emits electrons. This particular phenomena we call it as photoelectric effect. And that plate whatever is taken up there is called photocathode. The electron whatever is emitted over there is called photoelectron. And ultimately the material of that photocathode, we call it as photosensitive material. This of course is known to all of you. And this particular photoelectric emission can be explained only by considering Max Planck's quantum theory. That means Newton's corpuscular theory like, Huygens wave theory like, Maxwell's electromagnetic wave theory like theories cannot explain photoelectric effect. So Newton's corpuscular theory cannot explain, Huygens wave theory also cannot explain, Maxwell's electromagnetic wave theory also cannot explain photoelectric effect. Only one theory it can explain it, that is Max Planck's quantum theory. Using that quantum theory concepts, Einstein has given a photoelectric equation which all of you are familiar with. H nu is equal to W naught plus half mv square. If you recollect once again, H nu is the energy of the incident photon. W naught is work function of the photosensitive material. Half mv square we call it as the kinetic energy of the emitted photoelectron. So in fact most of our problems are directly based on this formula only. And all of you are very much familiar with the other version of this equation also. H nu can be written H nu naught plus half mv square also. Out of that, this nu naught is called threshold frequency. That is the minimum frequency of incident light required for the photoelectron to be emitted from the surface of that photosensitive cathode or photosensitive material. That's the point. So most of our problems are based on these equations only. So let us once again try. As we go on from problem to problem, we may be coming across different ways of applying the same formula to solve each and every model question there. So let us take the next number, that's problem number 4. It is based on photoelectric emission. Let me read out once again what has been given. A photometal is illuminated by lights of wavelengths lambda 1 and lambda 2 respectively. So according to his values, lambda 1 and lambda 2 are two different wavelengths of light which is incident on the same photometal. Remember that, not on different metals. That means same photometal means one should understand the work function of that metal is going to be constant. The moment you read the first sentence, you should immediately get to your mind that the work function of that metal is going to be constant. That's one area you have to concentrate on. Come to the second. Let us continue the second part of the problem. The maximum kinetic energies of emitted photoelectrons, right, are E1 and E2 respectively in these two cases. E1 is the kinetic energy 1 what has been given, and E2 is the kinetic energy of the other electron what has been emitted when this wavelength light is incident on the photocathode. Now what is the question he is asking? Obviously he will ask only one value, that is what is the work function of the metal. The work function of the metal is how much? Like in the form of a formula we will be getting nothing else. What are the four options given? Let me read out first. The very first option says E2 lambda 1 minus E1 lambda 2 whole divided by lambda 1. Second option says E1 lambda 1 minus E2 lambda 2 by lambda 1 plus lambda 2. Third option is given this way, E1 lambda 1 minus E2 lambda 2 divided by lambda 1 minus lambda 2. And fourth option has been given this way, E2 lambda 2 minus E1 lambda 1 divided by lambda 1 minus lambda 2. So these are the four options mentioned. Right, let us check which is the correct option out of the four for us according to the data provided. So lambda 1 is the first wavelength, lambda 2 the second wavelength. E1 is the first kinetic energy, that is kinetic energy of the first electron emitted when lambda 1 is the wavelength of incident light. And what is E2 here? Kinetic energy of that electron emitted when the wavelength of incident light is lambda 2. That is the point. So let us write this equation twice. The very first equation I am writing, hc by lambda 1. All of you can understand h nu can now be written as hc by lambda. So hc by lambda 1 must be equal to work function of the material, that is W naught, plus half mv square for that corresponding electron is given in the problem as E1. So you can write hc by lambda 1 is equal to work function plus the kinetic energy of the emitted photoelectron. That's what is the first equation. Now let us write for this pair of values the second equation. hc by lambda 2 is equal to again W naught plus this time the kinetic energy of the emitted electron. Let us write it as E2. Already you might have observed in both the cases, I am not changing one value, that is W naught. Why am I not changing? You can directly understand. It is on the same metal, both the lights are incident. Even though their wavelengths are different, the material onto which the incidence is taken up, that material is the same. Then automatically you can all understand the material's work function also is going to be constant for any amount of light or any wavelength of light that is going to incident on that metal plate as such. So you can now say this being the equation 1 for us, this being the equation 2 for us. And our concentration is on W naught now. So simplest way of just solving this one is take the ratio. Just divide the first equation by the second. Then hc gets cancelled. You are going to get lambda 2 by lambda 1 is equal to W naught plus E1 by W naught plus E2. Look at once again this over this. hc gets cancelled, lambda 2 by lambda 1 towards my left. Towards my right, W naught plus E1 divided by W naught plus E2, that is actually the ratio. And out of that, W naught is the one which we have to estimate. Let's cross multiply and finalize the value. So it now becomes W naught lambda 2 plus lambda 2 E2 is equal to W naught lambda 1 plus lambda 1 E1. Now according to the options given, you just go ahead with the remaining calculation. He is giving almost in every option lambda 1 minus lambda 2 in the denominator. So lambda 1 minus lambda 2, bring this one this side. Directly you people can take up lambda 1 minus lambda 2, this W naught lambda 2, you take that side. Then that becomes now W naught into lambda 1 minus lambda 2 is equal to lambda 2 E2 minus lambda 1 E1. And of course you can understand what is the value we just want. What is W naught? That's all. So directly I can say lambda 2 E2 minus lambda 1 E1 whole divided by lambda 1 minus lambda 2. This is ultimate result for us. Lambda 2 E2 minus lambda 1 E1 by lambda 1 minus lambda 2. So bring this one W1, lambda 1 minus lambda 2, this comes over here. See the options given over there. Exactly the same value you are having in the fourth option given. Look at E2 lambda 2 minus E1 lambda 1 whole divided by lambda 1 minus lambda 2. So E2 lambda 2 minus E1 lambda 1 divided by lambda 1 minus lambda 2. So what is the correct option for this one? The answer for this particular problem is going to be D for us now. So what we should understand here, application of the same Einstein's photoelectric equation. But in terms of wavelengths, we people are just writing the corresponding equations there. So this is the method we people have to adopt to just get the value of work function if it is given in this model question. Like this is problem number 4, for which the correct answer is the fourth option for us, that is E2 lambda 2 minus E1 lambda 1 whole divided by lambda 1 minus lambda 2 as such. That is fourth problem. Let us check one more problem based on photoelectric emission only, that is problem number 5 again. Photoelectric emission is observed from a metallic surface for frequencies nu1 and nu2 of the incident light rays, out of which nu1 is greater than nu2, that is given there. If the maximum values of kinetic energy of the photoelectrons emitted in the two cases are in the ratio 1:k, then the threshold frequency of the metallic surface is how much? One of the excellent models again. Equation is the same, but how to tackle the model, that just differs a little. Options are given this way. The first option is nu2 minus nu1 by k minus 1. And second option is k nu1 minus nu2 by k minus 1. And third option is k nu2 minus nu1 by k minus 1. And fourth option is given nu2 minus nu1 by k. What is the correct option for this? We just have to decide. Once again, if you look at the wording, photoelectric emission is observed from a metallic surface for frequencies nu1 and nu2 respectively of incident light. Nu1 is the first frequency, the frequency of the first ray, and nu2 that are the second, and he gave us a relation that nu1 is greater than nu2. Nu1 is greater than nu2 means what? Very simply speaking, the kinetic energy of that electron which has been emitted is going to be more in the first case than in the second. Like because kinetic energy of emitted electron is directly proportional to the frequency of incident light that is incident on the metal. So you can understand here that is the relation. Nu1 is greater than Nu2 means kinetic energy of emitted electron in the first case is greater than the kinetic energy of the emitted electron in the second case. Now come to the next one, please. If the maximum values of kinetic energies of photoelectrons emitted in the two cases are in the ratio 1:k. So I can directly write this way, Ke1 by Ke2, that is given as 1/k. So what can we write now from this one? Kinetic energy 2 is equal to K times kinetic energy 1. That is the relation what we people can predict out of the second sentence what has been provided to us. Then what is his question? Then threshold frequency of the metallic surface is how much? Threshold frequency, that is nu naught, he is asking you to calculate. So if you look at this once again, what is the first equation I can write? H in nu1 is equal to H in nu naught plus kinetic energy 1. I can write like this as the first equation. So this is my first equation for the incident light having a frequency nu1. I can rewrite that Einstein's photoelectric equation in this form. What about the second one now? I can now write H in nu2 is again H in nu naught plus kinetic energy 2 now. Now you can rewrite the same equation this way, H in nu naught plus what is kinetic energy 2 according to the given value? It is K times the kinetic energy of the first case. K times kinetic energy in the first case. That's what actually we have been given here as a relation. I have taken the same relation. I have written it like this. Accordingly, I am substituting in place of Ke2 as K times Ke1 like. That's my second equation. Now what is it we want? We just want the value of nu naught, nothing more. We want the value of nu naught means it's better to directly substitute the value of Ke1 into this. That of course you can do in different ways. You can solve these two equations. Otherwise directly write Ke1 and substitute that one here and simplify the things. So what can we write now in this case, please? Ke1 by K times Ke1. This over this, I write that one as H into nu1 minus nu naught by H into nu2 minus nu naught. Just look at this equation carefully. Ke1 is H into nu1 minus nu naught. This K times Ke1 is now going to be H into nu2 minus nu naught. H gets cancelled, Ke1 gets cancelled, you are left with 1 by K. That only what has been given there. So now cross multiply this one and finalize your result. So nu2 minus nu naught is equal to K nu1 minus K nu naught. Cross multiplication. Now what is it we just want? We want the value of nu naught. But if you look at the options once again, he is just giving you K minus 1 like he is giving. So bring that one this side. So this implies nu naught into K minus 1 is equal to K nu1 minus nu2. And my concept is, what is nu naught? The question. Nu naught is now K nu1 minus nu2 by K minus 1. This is the outcome of this calculation. So nu naught is equal to K nu1 minus nu 2 divided by k minus 1. Look at the options given. The second option is exactly tallying with this outcome what we have got after the calculation part of it. So what is the second option? K nu 1 minus nu 2 divided by k minus 1. That only we have got here. So we can outrightly say that the correct option for this one is going to be the second option, which of course is k nu 1 minus nu 2 divided by k minus 1. That is actually the concept. So same equation once again, Einstein's photoelectric equation only is the one which we are having in this topic of photoelectric effect. But how best we used to rewrite that equation according to the given values, it all depends on that. Equation is only one, but the same equation in different ways we people used to rewrite. Those points we should be rather careful enough. That's all. So the fifth question, as far as our order is concerned, that has got the option as B. That is of course the same what has been given there in the 4 option space. So this is problem number 5 for us. The next number, problem 6. The maximum velocity of an electron emitted by light of wavelength lambda incident on the surface of a metal of work function phi is how much? It's just asking you maximum velocity of an electron emitted by light of wavelength lambda incident on the surface of a metal of work function phi is how much? For that he has given us some letters which are needed there in the formula. One, of course, small h he has given as Planck's constant, m he has given as mass of the electron, and c, small letter c, that is speed of light he has given. And options are given this way: square root of 2 into hc plus lambda phi divided by m lambda. The second option is 2 times hc minus lambda phi divided by m. The third option is square root of 2 into hc minus lambda phi divided by m lambda. Only difference between the first option and third option is there you are having positive sign between the terms and here negative sign, that's all. And fourth option is twice square root of twice hc lambda minus phi divided by m. So these are the 4 options provided to us. Let us once again work out what is the correct answer for this problem. We want maximum velocity of an electron emitted by light of wavelength lambda incident on the surface of a metal of work function phi. So you can understand here work function is given as phi. Then what can I write now? hc by lambda is equal to work function plus half mv square. That is the formula. That V he is talking about as the maximum velocity. When kinetic energy of the electron emitted is maximum, automatically the velocity of that emitted photoelectron also will be maximum. So he is asking us to calculate this velocity from this data. Now come on, write that one once again here. It is half mv square, that is V maximum square, that is equal to hc by lambda minus phi. Simple calculation, nothing special there. So you can write this one hc by minus lambda phi by lambda after taking LCM of it. Then what will now be the value of V maximum square? This now becomes 2 times hc minus lambda phi divided by m lambda. And what is next step? You directly can understand, that is our answer. V maximum, maximum velocity of the emitted photoelectron he is asking us. So V maximum now becomes square root of 2 into Hc minus lambda phi whole divided by m lambda. This is supposed to be the equation for maximum velocity of the emitted photoelectron. Now if you look at all the 4 options, see the third option now. 2 times Hc minus lambda phi divided by m lambda whole under root. So same option has been given as the third option over there in the problem 6. Therefore, we can say the correct answer in this particular case is C like. So the equation once again is same. H nu is equal to W naught plus half mv square. That only in a slightly different manner we people have just taken up here. That is problem number 6 for us what we have. Let us just continue with the next number now. That is problem number 7 for us. The threshold frequency for a certain metal is nu naught. When a certain radiation of frequency 2 nu naught is incident on this metal surface, the maximum velocity of photoelectrons emitted is 2 into 10 power 6 meter per second. If a radiation of frequency 3 nu naught is incident on the same metal surface, the maximum velocity of photoelectrons emitted would be how much? But in fact, we all know for this photoelectric emission to take place, the basic condition is that the frequency of incident light should be greater than the threshold frequency of that metal. So if you can understand that one, this problem easily you can work it out. Work function is given according to the threshold frequency. That's given nu naught here. And what is the frequency of incident light he gave? 2 nu naught he has given in the first case, 3 nu naught he has given in the second. And what are the 4 options he has mentioned? Let me read them out first. First option, 2 into 10 power 6 meter per second. That means there will be no change. That's what he is talking about in the velocity of that electron emitted. In both the cases, there will not be any change. Second option says 2 root 2 into 10 power 6 meter per second. That's the second option for us. And third option is given 4 root 2 into 10 power 6 meter per second, and fourth option is 4 root 3 into 10 power 6 meter per second as such. Okay, let us work it out once again. Which one is correct out of the 4 options? We automatically will come to know that. The frequency of incident light is given 2 nu naught. So first you write the first equation. H times 2 nu naught is equal to H nu naught plus half m V1 square. You write like this. What for I have written like this, you all can understand straight away. This in fact is the kinetic energy of the emitted photoelectron. And V1 is corresponding velocity of that photoelectron which has been emitted. So this is in the place of work function we have written. This is actually the energy whatever is incident on it. And half mv1 square is the total kinetic energy or maximum kinetic energy of that photoelectron which has been emitted now. So what can we write now from this one? You see first. Half mv1 square is equal to h into 2 nu naught minus nu naught. I now can rewrite the same as h nu naught. That is my first equation. Look at once again, half mv1 square is equal to 2h nu naught minus h nu naught. It is as well equivalent to h nu naught. That's the first one. What about the second equation now you look at? What is incident frequency here? 3 nu naught he gave. So let us write that one. H times 3 nu naught is equal to h nu naught plus half m v2 square. Let me write that equation like that. v2 is now the maximum velocity of that emitted photoelectron when the frequency of incident light is 3 nu naught. So we once again can rewrite the same equation this way, that half m v2 square is equal to h, if you take common, 3 nu naught minus nu naught, which now becomes 2 times h nu naught. That's my second equation. In fact, this is 2 nu naught into h nu naught. I can write it like that. Now simply take the ratio of these two. What is it you are going to get now? From 1 and 2, I am in fact dividing one by the other. I get v1 square by v2 square is equal to 1 by 2. h nu naught by 2 h nu naught getting cancelled, we are left with 1 over 2. You can even rewrite the same this way, v1 by v2 is equal to 1 over root 2, taking root on both sides. My concentration now is on the velocity 2. So you can cross multiply that one to get v2 is equal to root 2 times v1. But what is the velocity of the first particle, first electron that is emitted he has given? It is 2 into 10 power 6 meter per second he gave. So rewrite the same thing now. It's root 2 times 2 into 10 to the power 6. So what ultimately will now be the value? 2 root 2 into 10 to the power 6 meter per second. That is the corresponding value for us. 2 root 2 into 10 to the power 6 meter per second. Which option is coinciding with that? You look at once again. The second option is given exactly the same there. 2 root 2 times 10 to the power 6 meter per second. So automatically second option is going to be the correct option for it. So I can write answer in this case is going to be B now. So you can just understand once again we are using the same formula. H nu is equal to W naught plus half mv square is the only equation what is to be taken up while working out any problem on photoelectric effect. But the same formula, at times we change the versions, that's all. So in this case also, using the same equation of Einstein, we just have calculated what is the velocity in the second case of the emitted electron. That of course is 2 root 2 times 10 power 6 meter per second, which is coinciding with the second option here. Therefore our answer is going to be B for this problem number 7. Let us check the problem 8 please. The kinetic energy of photoelectrons is E when the wavelength of incident light is lambda by 2. The kinetic energy becomes 2E when light of wavelength lambda by 3 is incident on it. The work function of the metal is how much? So he is giving us two separate pairs of values. When light of wavelength lambda by 2 is incident on the photometal, then kinetic energy of the emitted electron is given as E. And when the wavelength is becoming lambda by 3 this time, then he is talking about the kinetic energy of that emitted photoelectron has become 2E according to the problem given. And what is W naught? The question. W naught is nothing other than work function in this particular case. What is that value? That's what we just have to take up. So what can we write now? Write the first equation first. Hc by lambda by 2 is equal to W naught plus E. That is your first equation. Hc by lambda is work function plus kinetic energy of the emitted photoelectron. Exactly like that, if you take the second one, Hc by lambda by 3 this time is now becoming W naught plus 2E. Only thing you should now look into is how he is providing us the options in terms of which values he is giving us the options. Let me read out the first option given, Hc by lambda. Second option, 2Hc by lambda. Third option, 3Hc by lambda. And fourth option, Hc by 3 lambda. So observe very carefully, he is giving work function in terms of H, C and lambda respectively. But we don't have this letter E anywhere in that problem, in those options I am talking about. So simply eliminate E and finalize your answer. So what can we write now from this one? The first equation says E is equal to 2Hc by lambda minus W naught. That value you substitute it here. So what can we write now? This I take it as equation 1, this I consider it as equation 2. Now substituting 1 in 2, what is it I am going to get? You can understand this way now. 3 times Hc by lambda is equal to W naught plus 2 times E. Now you can write this one 2 times this whole, that is 4Hc by lambda minus 2W naught. So what else you can do now? This of course becomes 4Hc by lambda minus W naught. And our concentration is only on W naught. So this implies W naught is equal to 4Hc by lambda minus 3Hc by lambda, that ultimately becomes Hc by lambda. So what is work function, the question? We people are getting that one as Hc by lambda. Out of all the 4 options given, the very first option is in coincidence with the same outcome of this calculation what we have got. So what can we write now? The answer for this particular problem is going to be A. So only thing once again is H nu is equal to H nu naught plus half mv square, the original form. Same we people have written in terms of Hc by lambda is equal to W naught plus the kinetic energy of the emitted photoelectron as such. So equation is same but in a different orientation. With a different orientation we people are writing that one, nothing more. So this is problem number 8 what we have. For that the answer is the first option, which is Hc by lambda as such. Now the next number is problem 9. Work functions of 3 metals A, B and C are 4.5 electron volt, 4.3 electron volt and 3.5 electron volt respectively. If light of wavelength 2500 angstroms is incident on the metals, then what happens? Of course 4 options have been mentioned there. In the first option he says photoelectrons are emitted from A only, that is the first metal only. Second option says photoelectrons are emitted from B only, that means only from the second metal, not from first and third. Third option says photoelectrons are emitted from C only, not from the first metal, not from the second metal, only from third metal the electrons are emitted. And come to the last option, that is given as the fourth option please. Photoelectrons are emitted from all the 3 metals, from A, from B as well as from C. That's what is the conclusion he is making by giving the fourth option like that. but in fact we do not know which is correct there. This question has been asked way back in 2001 in IIT exam, IIT paper. So one should understand here, for photoelectric emission to observe, if we want to observe photoelectric emission from a photosensitive material, what is the basic principle? What is basic principle here? The energy of incident photon in the form of light, I am talking, the energy of incident photon should be greater than the work function of the metal. I once again repeat, this in fact is the basic concept for us to identify whether photoelectric emission takes place in a particular metal, in the case of a metal or not. What are the basic thing here? If the energy of incident photon is greater than the work function of that metal, what has been taken up there, certainly photoelectric emission takes place. By any chance, if the energy of incident photon is either equal to the work function of the metal or less than the work function of the metal, photoelectric emission will never take place. So one should understand that photoelectric emission takes place only when the energy of incident photon is greater than the work function of that photosensitive material, what has been taken as photocathode there. So what is the calculation here? 2500 angstroms of light is now incident on each metal, like he said. So wavelength of that light, whatever is falling over there, is 2500 angstrom units. What is the corresponding energy of this light? You calculate, that's all. What is energy of this corresponding light, please? Hc by lambda. All of you can understand, this is light, means it is photon I am talking about. A photon of wavelength, this one is incident on the photometal. Then what would be its corresponding energy? Energy E is equal to Hc by lambda. But most of you must be knowing there is a shortcut method for this calculation. Actually, the value of Hc and lambda when you consider lambda directly in angstrom units, then you can write this one 12,400 divided by lambda taken in angstrom units. But in true sense, you must all be knowing the correct value of it also. It is actually 12,412. But we people used to approximately write that numerator value 12,400 divided by lambda taken as it is in angstrom units. Then what will you get, you know? You will get energy in electron volts you will get. So this calculation is to be taken up only when you want the energy to be worked out in electron volt units. Suppose if you want the value in joule, simple. After getting the value in electron volt, multiply that one by 1.6 into 10 power minus 19 joule. Because all of us we know 1 electron volts equivalent energy in terms of joules is 1.6 into 10 power minus 19. That of course is a charge on an electron times joules. So if you can understand here, I can directly take up this calculation. E is equal to 12,400 divide 2,500 you take. Don't convert this one into meter or centimeter. Take as it is in terms of angstrom units. So you can cancel these things off. Had it been 125, I would have got exactly 5 times. But it is 124. That means certainly the value will be nearly 5. What? Electron volt. In fact, I am not calculating true value there. It takes time also for us. So, best suitable thing is 124 by 25 is nearly 5. I can take it for granted. Now, you see, for the first metal A, what is work function given? What is the work function value for the first metal given? It's 4.5 electron volt. Now you can see the energy of incident photon is greater than its work function. The moment it is greater than its work function, surely photoelectric emission takes place. That means photoelectrons are emitted from the first metal now. So, from the first metal, we can find photoelectric emission possible. Now, check the second one. For the second metal B, what is the work function he has mentioned? Check once again the value. 4.3 electron volt he gave. Once again compare the value. This energy of incident photon is again greater than the work function of the second metal also. That means what is your conclusion? From second metal also, photoelectrons can be emitted out now. And what about the third? For C, the metal C, work function has been given this time as simply 3.5 electron volt. In fact, you can see this is less than even these two values. So, once again reiterate the same wording. What is that? The energy of incident photon, since it is greater than the work function of this metal C also, you can say photoelectrons are emitted from the third metal also. So, first option is not going to be true. Second is not correct. Third also is not correct. What for? He is talking in the first case only from A, photoelectrons are emitted. In the second option only from B. Third option only from C. So, all the three options are not correct. Then automatically the fourth one only is left. What is that? Photoelectrons are emitted from all the three metals. That of course you can understand here. The incident energy of the photon is greater than the work function of individual metal there. The moment it is like that, automatically photoelectric emission takes place. So, what is the corresponding answer now for us? The correct answer for this one is going to be D. So, the energy of incident photon is greater than work function of A, work function of B as well as work function of C. Therefore, possibility for emission of photoelectrons is there for all the three metals. So, all the three metals without any doubt photoelectrons they emit. That is the concept. So, correct answer for this problem 9 is going to be the fourth option, that is D. So, I think all of you might have understood how to just identify whether photoelectric emission takes place when we consider a metal over there or not. That is the criteria for us. So, this is problem number 9. Let us check the next number, that is problem 10 for us. The work function of a substance is 4 electron volt. The longest wavelength of light that can cause photoelectric emission from this substance is approximately how much? One of the excellent questions which has been asked way back in 2004 IEEE paper. The longest wavelength of light that can cause photoelectric emission from this substance is approximately. Observe the wording first of all. Afterwards, I will just read out the 4 options. You know what is the threshold frequency? What is threshold frequency? The minimum frequency of incident photon that is needed for the metal to emit a photoelectron from its surface. That is the minimum frequency. Underline the word minimum there. Corresponding to that, when we talk about threshold wavelength, What is threshold wavelength? It's not minimum. When frequency is minimum, automatically wavelength will be maximum, because nu is equal to c by lambda. So if you look at this nu and lambda, they are reciprocals of one another, they are inversely proportional. So what we people should understand here, if you take the maximum wavelength, that is nothing other than threshold wavelength he is asking. So work function W naught, you can write it as h nu naught and hc by lambda naught. What is this nu naught here called now? This is called threshold frequency. Threshold frequency. And what is this lambda naught called? That is what we call it as threshold wavelength. And also you should understand here is threshold frequency is nothing other than the minimum frequency of photon that is required for this photoelectric emission to take place. And threshold wavelength means it is to be taken as maximum wavelength. That is the concept. So threshold frequency and threshold wavelength, when you talk about, maximum wavelength is threshold wavelength, minimum frequency is threshold frequency of what? Of that photon which is now incident on the metal for photoelectric emission to start with. So this is actually the concept. Now we want this lambda naught. So what can I write now? Lambda naught is equal to hc by W naught. Just now I have told you the shortcut method over here. That hc, I can now write directly this one as 12,400. By lambda naught, this W naught, you directly write that one in electron volt only. Don't convert that one into joule. Don't convert that one into any other units other than electron volt. If you do like this, you will be getting the answer in angstrom units. Already we have discussed it the other way earlier. Now we are talking about 12,400 by W naught taken in electron volt, that gives you wavelength directly in angstrom units. So what can we write now? This is equal to 12,400 divided by, what is the work function that has been provided to us? It is given 4 electron volt. Write directly 4. Don't convert that one into joule, I said, therefore take 4 directly in electron volt. So what happens to this? You will be getting 3100 angstrom units. 3,100 angstrom units we people are getting for the wavelength of the incident photon. Fine. But what are the options he has given, you see? First option says 340 nanometer. Nano is 10 power minus 9, we all know. Second option is 400 nanometer. Third option is 310 nanometer. And fourth option is 220 nanometer. So what is this angstrom? We all know it is nothing other than 3,100 into 10 to the power minus 10 meter. That is actually the wording. But angstrom is 10 power minus 10 meter. That of course he is asking you in nanometer. 10 power minus 9 I want. So what we can write now directly in this case, please? It now becomes 310 nanometer. If you write 310 nanometer, 310 into 10 power minus 9, multiplying and dividing by 10, you will be getting exactly 3100 angstroms. So if he asks you the answer in meter, you can write it this way. If he wants the answer in angstroms, you can directly write it this way. But he is not asking you both of them. He He is asking us to write in terms of nanometer. So 310 nanometer must be the corresponding maximum wavelength, which is called threshold wavelength of that material used as photocathode. So which is the correct option here? Third option, C, is given 310 nanometer. So correct answer for this particular problem is going to be C, according to the given 4 options for us. So this is problem number 10. Only thing you should understand is minimum frequency when he asks, it is threshold frequency. Of what? Of the incident photon I am talking. Maximum wavelength of incident photon, suppose if they ask, that is to be called threshold wavelength. If you can identify the difference of these between these two, it's going to be a very, very simple problem for every one of you. That is problem number 10 for us, for which the answer is C, that is 310 nanometer.